to start. I do apologize for slight delay. There's always technical issues. Today it's my great pleasure to introduce our speaker, Torben Kunis, and he is at the University of Stuttgart, Institute of Flight Mechanics and Controls. He also has a adjunct appointment in our aero department at the University of Michigan. He got his PhD degree at the University of Toulouse in 2019. He was a researcher at ONERA. This is a French aerospace lab, and he was also here for a few years in aero department as postdoctoral research fellow. His research focuses on algorithmic systems and control theory, with a focus on nonlinear optimization algorithms and verifiable nonlinear control systems.
Yeah, thank you very much, Ilya. Very happy to be here. As Ilya said, I've been here before, a long time ago. I'm not sure when was the last time I've been physically in the control seminar. Probably sometime early 2020 before it went into lockdown mode. Since then, I've worked on a lot of different fields and problems, but predominantly on systems theory and nonlinear optimization. And in my talk today, I want to show you a little bit when these two come together and what we can say about nonlinear optimization from a systems point of view. Let's start with a small example, actually two different ways of viewing at an optimization problem. I show you where the dynamics come into here. Now on the left-hand side, that would probably be the traditional way of viewing of an optimization problem. This is a slingshot maneuver. Maybe NASA plans to do that for some interplanetary mission. There you solve meticulously an optimization problem. You do this years in advance. You really figure out at which time you have to be where in between these planets to get the most out of your slingshot maneuver. And as I said, you do this years in before. You've got lots of time to solve the optimization problem. And then you solved it, and it's a job done. You just apply the solution. Of course, you have to wait for the next launch window, and then maybe the window passes, and maybe you have a backup solution, so maybe you solve this twice. Okay, fair enough. But it's a on-off event solving this kind of optimization problem. Opposed on the right-hand side, suppose you want to solve a navigation maneuver or a navigation problem. You want to go from A to B. Now, traffic is highly dynamic. All of you who are stuck in a traffic jam knows that. So what's happening is you solve this problem once, Google says, okay, you should go this way, and then you start driving, things change, you re-solve the problem every time. So you keep solving an optimization problem while your environment changes. You change your position, other cars change your position, maybe there's an accident on a neighbor road, all the people are coming to your road, so maybe you avoid the road you're on, etc. And this is the way of thinking of optimization problems that I want to look at, or that I'm looking at most of the time, and I want to talk today. What's happening if optimization happens repeatedly, if it starts getting a dynamic of itself? The architectural view that I'm going to adopt here is a bit of that. We've got some kind of optimization here, and really there are plenty of examples for that. You could have an optimal control problem, you might have some convex optimization problem, you have a neural network that you train, any kind of optimization problem you can think of. And then on the upper level, you got some kind of high-level decision-making device. Now, this high-level decision-making device could be a dynamic system, it could be some user operator, it could be a central unit if you think of distributed optimization, it could be some hyperparameter optimization in neural network training, so you have some higher-level objective that you want your trained network to satisfy, etc. And now what's happening is that this higher-level decision-making unit is propagating some kind of parameters to your lower-level optimization problem. You solve the optimization problem, and the solution is propagated back to your central unit, and the central unit makes a new decision based on the previous solution. That's all fine, as long as you assume that the solution you're getting back is exact. And often we do that. When we think of these kind of loops, think of model predictive control, we assume the solution we are getting from the optimization problem is exact. Now, there are several reasons that why this assumption might not be satisfied. And the most general form is there's some kind of disturbance. Think of MPC, you're under real-time constraints. You're not very likely to get a very exact solution. You have to stop the optimization problem at some point. You're getting an inexact solution back. It's one form of disturbance that's affecting your optimization problem. You could also have mismatch in your data. Wrong model data affects your solution from the actual true solution. So somewhere in this loop, from solving an optimization problem and making a decision based on the solution, where formerly we depended on the fact that the solution was exact, gets thrown off by the fact that you have some kind of disturbance in the lower level. Give you a few more examples here. I've talked about it already. Model predictive control. You have this bi-level structure. You solve an optimal control problem, which is parameterized in the current state of some dynamic system. You get an optimal control solution from it. You apply the optimal control solution to your dynamic system. The dynamic system is doing something when you control it. You take another state, you resolve your optimal control problem. Think hyperparameter training. You solve a least square problem on your neural network, given some data under some parameters, but then you also want to minimize some cross-validation accuracy. Typically, you do that by some kind of subgradient descent on the higher level. And that gives you a new parameter set and you resolve the training. You can even think of, and that actually is the nice thing about this, you can think of certain optimization methods, such as augmented Lagrangian method, also in this kind of structure. You're solving an optimization problem. Here the problem of minimizing the augmented Lagrangian unconstrained, subject to a dual variable. And then whatever your optimal primal variable is, you make a change in your dual variable. You repeat the underlying primal optimization problem. So this kind of dynamics in the loop for an optimization problem happens in optimization itself. I really like this fact. Okay, the fundamental question now is, I said everything's usually fine as long as there are no disturbances, but no disturbances isn't really a realistic setting. We know that in controls. So what's happening when we have a disturbance and the disturbance starts affecting the interconnected dynamics of our optimization in the loop? That's kind of the fundamental research question that motivates all this work. And the system theoretical concept that I've been using to answer this question that I want to talk about today when we think of systems theory is the concept of input-to-state stability, for short ISS, introduced by Eduardo Sontag some 40 years ago now. And it encapsulates very nicely a couple of properties for nonlinear systems. The optimization problems we're looking at, but these type of optimization algorithms typically form some kind of nonlinear dynamics. Most notably, it combines two notions. One is the notion of asymptotic stability of the undisturbed dynamics. And second is the notion of some asymptotic gain. Whenever you have some disturbance, and disturbance here can be a time-varying signal, you have some disturbance affecting your ISS dynamics, then in worst case, the deviation of your dynamic system states will still be bounded by some monotonic function in the supremum's norm of your disturbance. That means, as part of it, you get some kind of practical stability, and the radius of this practical stability is determined by the worst value of your disturbance. And if in asymptotic, your disturbance is going to 0, you're still kind of stabilizing on this decreasing practical stability radius, which means if your disturbance goes to 0, your overall dynamics go to 0 as well. You kind of recover the asymptotic stability. Now, to make this clear, I present this here for global asymptotic stability and global ISS. The notions we will use today, or the properties we derive today, are all local. And I comment on that a little bit later. Why is ISS useful? ISS is useful because it's very powerful in applying or extending notions of ISS into interconnections. Suppose we got two systems which are ISS. We've already established that. We can construct a feedback interconnection, and the feedback interconnection will be ISS as well, as long as the so-called small gain condition is met. Small gain condition means these two gains that we introduced on the previous slides, they must be smaller than identity, or if these are scalar gains, the product of the two must be a number smaller than 1. Even better, if you had some kind of cascade, you have no feedback, but just a kind of unilateral connection of two ISS systems, then the result is always ISS, no questions asked. So it's a very powerful concept to extend from stability on a component level, or robust stability on a component level, to robust stability of the level of interconnection. And this idea has been used in the literature a couple of times by myself, but also by a few of previous researchers that have influenced my work. And some of the results we can obtain if you have ISS in the optimization algorithm is, for example, that an MPC algorithm is still asymptotically stabilizing, even if we solve the lower level optimal control problem with a limit on the number of iterations we can do. It's one of the applications here. And similarly, if we talk of this in a greater level of optimization, if you have a bi-level optimization scheme, multiple optimization problems affecting each other, we can have similar results. We can have inexact lower level solutions. We even can have inexact gradients in our problem formulation that stem from the fact that we're inexactly solving some problems, and we are still going to converge to some bi-level optimal solution. And we can further extend this to problems where there isn't differentiability in the first place. We're still trying to have some inexact gradients. Not going to talk about these results here, so it's all in the papers. I invite you to read them. Right. Now that we have the notion of ISS, we would ask, what optimization problems are actually, or which optimization algorithms are actually ISS? And under which assumptions about our problem data? And this has been another field of research here, where different people at different times looked at different algorithms and said, okay, this algorithm is ISS under this assumption, that algorithm is ISS under another assumptions. And it's quite distributed with all these different algorithms. Today, what I really want to talk about is what is kind of the fundamental concept that underlies it. When do we have ISS in a family of methods? What are the mathematics behind it? And to answer this question, I want to take one step back. I gave you a very brief but somewhat shallow introduction into a couple of concepts that will keep popping up all throughout the presentation. We start from the idea of variation analysis. Suppose we've got some optimization problem, fairly simple. We are minimizing some cost function over a closed and convex set of constraints, or over a closed and convex set, which is described by our constraints. And we'll assume that this cost function is once Fréchet differentiable continuously. Now, the first question would be, what's kind of the minimum value that our cost function takes on the constraint set? But more importantly, in the examples I've shown before, what we are after is what is a minimal solution. So what is the solution to the primal decision variables at which our cost function takes this minimum value? Think of the optimal control problem. The information that the minimum value of your optimal control cost is 0.5 doesn't really help you. You want to have the control strategy that actually achieves this minimum solution, right? And if our cost function isn't convex, we typically can't hope for a global solution. We will look for a local solution. We're asking, what is a local minimum, it's a local solution for our decision variables such that our cost function takes a minimal value on our constraint set? And then certainly a condition for that necessary and sufficient is that there exists some neighborhood such that for any other point on our constraint set intersected with the neighborhood, so basically around our optimal solution, the cost function is larger than or equal to the minimum value that we obtain on the optimal solution. And now we can shrink this neighborhood, we make it smaller and smaller, we get kind of a hyperlocal solution, and we get a condition which is basically a first order necessary condition. We say when we take the gradient, which by assumption exists and is continuous in the parameter, we take the gradient and we look in any possible direction from our local solution, then we are at most, or we are not decreasing, right? We might be staying the same, or we might ascend. Now this solution, this below here is what they call a variational inequality. And it basically means that our gradient as some kind of, as a linear operator, defines a hyperplane, and the hyperplane separates our constraint set from, well, the outside of the constraint set. Now, because the gradient as a linear operator defines the separating hyperplane, we can also say that the gradient is in the normal cone of our optimal solution with respect to the constraint set. Actually, vice versa, the normal cone of the constraint set at the optimal solution. Now, this normal cone is very well defined for any point x. And now that's kind of the leap I'm hoping everyone gets here, because that's going to be important. We can construct this normal cone for any possible point in our constraint set. We get what we're going to call a set-valued mapping. We get a mapping from any point x towards this sum here in the equation above, namely the gradient plus any possible value in the normal cone. And this has a set of values. So we have a mapping from a point to a set of values. That's why we call it a set-valued mapping. And this equation above becomes what we call a generalized equation. Now we are not after one solution to a single equality. We are after a solution where the set-valued mapping takes a set that contains the zero. Okay, we got this all from the first order necessary conditions that we derived by variation analysis on the slide before. The reason I introduced this is because the Karish-Kuntake necessary condition, which are necessary conditions for constraint optimization problems in primal or dual decision variables, can similarly be formulated as some kind of generalized equation. And same as before, a primal dual solution would be a solution to the KKT conditions if it satisfies such a generalized equation. For that reason, most of the nonlinear optimization algorithms that we would look at in the context of this work actually solve the generalized equation. They solve for a primal dual solution of the KKT conditions by means of solving this type of generalized equation, and don't directly attack the primal optimization problem that I introduced earlier. Which brings me to the topic of Newton methods. I assume you're all aware of Newton's method to solve an equation. What I introduced today is what could be considered a generalized Newton method, a Newton method to solve a generalized equation. The idea is very simple. We have the primal optimization problem on the left, necessary conditions on the right. We want to solve the generalized equation by Newton's method. What we do is we use an approximation, first order Taylor of our generalized equation, which means we have the gradient at some point xk that we have given. And then we take second order derivative and a linear mapping here. And this exactly corresponds to some quadratic problem in the primal problem. So solving the generalized equation by a first-order Newton's method equates to solving a quadratic problem in the primal problem. And that's exactly how SQP works. You take an approximation of your original nonlinear optimization problem. The approximation is quadratic. You solve the quadratic problem instead because we typically know how to solve quadratic problems. But really what we do is we do a Newton step for solving a generalized equation. And now from this Newton step, we get a very well-defined iteration. So we get a mapping from a possible solution xk to a new solution xk plus 1. Quite similar to Newton's method. Only distinction, this solution on the left is typically non-unique, or might not exist. Or it is unique, if it exists. So the underlying question now is, when is this Newton method going to be well-defined? In the sense of first, there exists a solution, and second, our solution exists. When does there exist a solution? And second, when does the solution or when does the iteration of solutions actually converge to where we want to go? Another way, when is this iteration going to be asymptotically converging? Which brings me to the last topic in this brief introduction, which is the topic of regularity. Regularity is a very broad framework. Again, I'm going to narrow this down later. But the idea really is we have these generalized equations. First, the necessary conditions on the left, which we're trying to solve for a solution by some kind of iteration. The iteration, again, could be understood as a generalized equation. And now we want to ask, when are these generalized equations or its solutions behave sufficiently nicely around our optimal solution? And with sufficiently nicely, of course, we mean, when does they behave so well that the iteration in the end is going to converge to our minimum? Or, in the question of perturbations, okay, maybe I shouldn't put this on the slide next. Or if we have some kind of perturbation, when is the perturbation don't affect our iteration too badly, too much? And the idea of regularity, I will mostly talk about strong regularity. I wanted to talk about metric regularity initially, but then I figured it's too broad of a concept. Talk about strong regularity, but intuitively what you can think of is some kind of combinations of surjectivity or openness of some operator, some kind of injectivity. In general, if you have a linear operator, think of a matrix, some non-singular linear operator. So basically some linear matrix operation, which you can invert a function that's bijective. So you have a well-defined inverse, etc. And the nice thing about regularity, and that's why it ties so beautifully to the type of system theory questions that we have been asking in the beginning, is that they are somewhat stable under certain classes of perturbations. So if our generalized equation has some regularity properties at one solution, and we don't perturb it too much, we keep our regularity notions. You might already see where this is heading to. Okay. In the next half an hour, I want to speak about 3 topics. First, what's happening under strong regularity to our optimization algorithms, or briefly, what are the type of results that we can have if we had strong regularity in the beginning, and what does it actually mean? Second, I'm going to try and characterize strong regularity in an optimization problem by means of the problem data. And then third, we're going to ask the question vice versa. What are actually sufficient system theoretical conditions such that we have these regularity properties? Or in other words, if we compare kind of the regularity in our optimization problem to the system theoretical notion that we get for optimization algorithm, are they somewhat equal? Is it much stronger of an assumption? Is it maybe weaker an assumption, etc.? Okay, let's start here. Now it's getting a little bit more mathematical. If you thought that was mathematical already, brace yourself. because we're going to be a little bit more general in what we discussed so far. Still, we are minimizing some cost function. I kept the notation. Now we're adding some equality constraint. And again, we have some more general convex and closed constraint set. We can do this in infinite dimensions. Most of the results I'm presenting here hold true. If you do it in infinite dimensions, if you really insist on doing that, you need some additional assumptions, as in your primary space needs to be asplund. You need some sequential normal compactness. I'm not going to go into details. These are just technical assumptions. Infinite dimensions, you typically can waive them. What we're going to assume all through this talk is we have already some local optimal solution. That was the assumption a priori. We have a local optimal solution. We want to figure out, are we going to converge there or not? Our cost function, the constraint function, are again continuously Fréchet differentiable. But importantly, we are not assuming, at least until here, we don't assume that we can do 2 times the differential, that we can compute a Hessian. And our constraint set is going to be non-empty, closed, and convex. Now, under some constraint qualifications, we can formulate necessary conditions for that, KKT conditions, and they take the form of these generalized equation, which lives in the primal and dual variables. And they are basically the first order necessary condition that I showed you before, plus constraint satisfaction of our equality constraint. And again, there's the normal cone, and then there's just a 0 below. Okay, just to quickly step out of the more general formulation, give you somewhat of an example. Maybe you've already seen some kind of optimal control problem, discrete time. Your primal decision variables would be a sequence of states and a sequence of input values. These states and inputs are tied by your discrete time dynamics. So you get a vector of equality constraints to make sure that your primal variables actually represent a sequence of states and inputs that matches together with the dynamics. And you typically want to find a solution, you want to find a control solution that minimizes some kind of cost function along the sequence, usually a weighted sum of squares of your states and inputs, maybe of the difference of your states to some target state, etc. And then your additional constraints typically come in the form of state and input constraints, usually upper and lower bounds on each of the values, more generally saying some kind of polygonals. This type of problem forms what I call a nonlinear program. It's a special type of the more general nonlinear optimization in the sense of you have finite dimensions, you're usually twice differentiable in your cost function and your constraint functions, and your convex set can be represented as linear inequalities. So you get element-wise inequalities as opposed to more complex convex sets. Okay. Let's get back to the more general problem. We want to solve this generalized equation, which characterizes our optimal solution by a generalized Newton iteration. Now, since we haven't assumed that we are twice differentiable, we have to replace the Hessian that we had in the slide before when I first showed you the generalized Newton's iteration. We have to somewhat approximate it. We're going to approximate it through this talk by some suitable operator H. If you think finite dimensional problem, that would be an approximation of your Hessian. Simply speaking, you would get some kind of quasi-Newton method. And for the remainder, whenever I introduce the Z, that's going to be the pair of primal and dual variables. Okay. Now we can form the Newton's iteration, and we actually get different types of optimization algorithms for different choices of the H. Just want to illustrate this here because later we're going to abstract and talk about arbitrary H's. I want to show you some examples. Say you do SQP, then of course your H would just be the second and first derivative of your Lagrangian and your constraint function, provided, of course, you had the Hessian. If If you wouldn't have the Hessian, then typically here you would have some approximation. Maybe you use some BFGS or something else to approximate the Hessian. Could also omit the Hessian part. Then you would actually get a sequential linear programming problem. So you would just use a first order linearization of your primal problem. We'll later see what's the caveats of this. And even some kind of projected gradient fits into this method. Although typically in this type of problems, you wouldn't have equality constraints. Still fits into this method. You just get some identity metrics scaled by your step length. Okay. Now we wanted to talk about perturbations. So your generalized equation might be perturbed in the sense that your functional part, which was the first order derivative, might have any kind of functional disturbance by your perturbation. And then this disturbance would propagate into your Hessian approximation. And generally speaking, you've had an additional input into your Newton's iteration, into this set-valued operator that defined your dynamics of the Newton's method.
Okay, quick.
Yeah, sure.
HP time as well, if you have like time rate, step size type thing.
Good question. Yes. If you're careful in the following derivation, it could. Yeah, no, certainly. You would probably want to deal then with some kind of uniformity notions. Or maybe even where would be able to make assumptions if you wouldn't have uniformity. But in general, it could be time varying. Actually, in some of the preliminary works, we assumed that the age itself would be the output of another dynamic, which would be the situation in a BFGS for an SQP. That would form basically a dynamic of itself, and you could study the interaction of the two. Okay, we introduced regularity again before, but for the sake of preciseness, I want to tell you a little bit what it really means. Definition of strong regularity of this set-valued mapping, in this case, the KKT conditions, means that there exists neighborhoods of your primal dual decision variables, as well as the output of your generalized, of your set-valued mapping, such that the inverse, just inverse in a classical function set, but now the inverse could be multi-valued as well, such that the inverse is actually single-valued around this pair Z bar V bar. So you pick a point in the graph of your set-valued function, and around this point in your graph, your set-valued mapping is single-valued. Again, if your set-valued mapping was a function all along, if it was single-valued all the time, then this condition would just mean that you had a bijectiveness. If you had differentiability, it would mean that your derivative was non-singular in a finite dimensional case. And in fact, basically corresponds to having some surjectivity and injectivity of your set-valued mapping. So the idea really is we have this unknown mapping, but the inverse is very well defined and it's single-valued. In the example here, we have the inverse of Z squared. So that would be strongly regular. So the Z squared as a mapping would be strongly regular at these 2 points up and down, because there you can kind of invert this, but then at the 0, of course, it wouldn't be strongly regular because the inverse would be multi-valued. Okay, then I really want to show you the result here. I'll tell you a little bit about how we derive it. So in the question of when is our generalized Newton method ISS, using strong regularity, we get 3 assumptions. First, of course, the point we're looking at must be a solution of our generalized equation a priori. Second, these combined functions of the function f, which was your first order necessary conditions, and your linear operator H must be uniformly Lipschitz continuous in all three inputs. Your three inputs here are the possible new solution, the previous solution, and your perturbation. And three, and that's where how good your approximation is comes into play. No, that's actually not true. And three, these generalized equation that you get from the approximation must be strongly regular. So you must have this invertibility, and it must be strongly regular with another constant defined by the Lipschitz constant of the inverse, where the product in between the constant here with respect to your, I think, previous solution and the regularity constant must be smaller than 1. If you had these 3.5 assumptions, then these generalized Newton's method, the iteration defined by the generalized Newton's method, would be locally unique and input to state stable in the sense as I introduced it before. And the way we would want to prove that, giving you the full proof here, but the idea is that under the assumption of strong regularity, together with the other assumptions, we have a solution mapping for the generalized Newton's method, which is itself unique and which is also Lipschitz continuous with the constant kappa times gamma. So if now we look at the difference between the new solution and our minimum that we want to find, we can rewrite this as two outputs of our solution mapping, and we apply the Lipschitz continuity property and get a function of the previous solution and the previous distance to the solution we wanted to find. And then because this product was assumed to be smaller than 1, this is essentially a dissipation inequality. Namely, it's a dissipation inequality that gives you ISS locally. The way this works, and I just want to briefly mention it, maybe also from an educational point of view, doesn't really, it's probably not crucial to understand the remainder of the talk. I hope so. The idea is that we are using what is called a generalized implicit function theorem, which means that if we define a solution mapping by another inequality, and the inequality we use to define the solution mapping is sufficiently regular and Lipschitz continuous, then this strong regularity propagates through to the solution mapping. It also means in order to study ISS of our generalized Newton method, what we really need to look at is regularity of our approximated KKT conditions in the first place. And if our approximated KKT conditions are sufficiently regular under the additional Lipschitz continuity and this small gain assumption, then this strong regularity is propagating through to our generalized equation, and we get the ISS result that we wanted to. Okay, but when are our KKT conditions actually strongly regular? You obviously want to ask this question. What does it mean from an optimization point of view? Well, we said it before. If you do generalized Newton's method, you typically do it in this structure. You have this linear operator H above, and you can partition it into your primal and dual decision variables. Lower right corner would typically be 0. And then strong regularity of these approximated KKT conditions actually amounts to an quadratic optimization problem having a unique primal dual solution. And this primal dual solution, again, must be Lipschitz continuous in the perturbation, where the perturbation here acts on your cost function as an additional linear term and acts at your constraint as basically the value your constraint must be. Right? So you have a quadratic optimization problem, you add a small perturbation to costs and constraints, And if the solution remains unique and Lipschitz within the perturbation, then you have strong regularity of your KKT conditions in the first place. Okay, this leads us to the more general question: when are the KKT conditions of an optimization problem strongly regular? For that, I want to go back to the nonlinear program that I showed you before, because here we have a very rich literature on notions of regularity and well-definedness of solutions. Nonlinear program, the way I understand it here is, again, you got finite dimensions, you got a cost function and constraint function that's now twice continuously differentiable, and your constraint set, for simplicity, is limited to the non-negative orthant. So all your inequality constraints are basically the primal decision variable is larger than or equal to 0. And of course, if we had these polygonal constraints I showed before, we can rewrite them in this type of inequality constraints. And in this case, if we look at the normal cone for the non-negative orthant at a possible primal decision variable, then this would be a subset of the non-positive orthant, where basically your normals could be possibly negative for any active constraint and would be equals to 0 for any component where you're actually positive. Now we need some constraint qualifications, pretty standard in the literature. The more general one is the Mangazari and Fromowitz constraint qualification, which has this somewhat ugly formulation, but basically what you need is your the derivative of your equality constraints is surjective, or vice versa, your gradients are linearly independent, and then it intersects somewhat nicely with your normal cone at the active constraints. If MFCQ holds at your primal solution, then there exists a dual solution that satisfies your KKT conditions, also bounded, but that doesn't matter right now. In addition, if the stronger linear independence constraint holds, which requires surjectivity or linear independence for all active constraints, then not only does there exist a dual solution, this dual solution is unique as well. There's a somewhat in-between constraint mode qualification that people sometimes call strong MFCQ. It's when MFCQ holds and your multipliers, your dual variables are unique, but LICQ might not hold. Anyway, the next concept from optimization theory that we need here is what's called strong stability. Now, strong stability is very similar to strong regularity, but it only covers your primal solution. The primal solution is called a stationary solution if there exist dual variables. I know this is horribly technical. I don't know who has invented that, but people use it. So a primal solution is a stationary solution if there exist duals to it, which satisfy the KKT conditions. And a possible stationary solution is called strongly stable if, again, some perturbed optimization problem has a unique stationary solution. And these function of stationary solutions for possible perturbations is, again, continuous, or actually calmness suffices, somewhat calm, continuous, around the stationary solution you're looking at. Okay. Now we got some nice results on the relationship between strong stability, strong regularity, and other properties in nonlinear optimization. First, by the Lipschitz continuity, we have that if our KKT conditions are strongly regular at the primal dual solution, then the primal solution is also a strongly stable stationary solution and MFCQ holds. The latter is a consequence of your dual variables being unique. And your dual variables are unique. If vice versa, no, okay, I wanted to pass it further. an optimal solution is strongly stable. That's actually equivalent to you have MFCQ and a strong second order sufficient condition holds. Second order sufficient condition typically is taking the Hessian of your Lagrangian on the subspace of some active constraints, and you get a positive matrix on the subspace. So this actually means an optimal solution that is strongly stable will propagate the optimality through the sufficient condition. So you have sufficiency around your stable solution. It's a very nice consequence, especially since, if you remember, strong regularity actually implies strong stability. So it kind of trickles down, right? And vice versa, if you have strong stability and you have linear independence, then you actually have strong regularity. So that kind of closes the loop, except for up there from strong regularity, we get MFCQ and uniqueness, but we don't necessarily get LICQ, or at least I'm not aware of it. So let's put strong regularity somewhat in context of more classical nonlinear optimization contexts. But what I've promised you was we want to ask the question, how does it actually compare to system theory? How does it compare to the generalized Newton's method being ISS? To answer this question, I'm going to introduce the perturbation into the optimization problem. So we have perturbations on our cost function again, and as on our equality constraint. Now this perturbation propagates through to the KKT conditions. And now this is really the disturbance that we added previously on the right-hand side of our KKT conditions when we talked about strong regularity. So strong regularity of the original unperturbed KKT conditions was really uniqueness of the primal dual variable for possible perturbations in our optimization problem. And since we've seen that by the implicit function theorem, all we needed for the perturbed generalized Newton's method to be ISS was this regularity property of the KKT conditions. This is really the only perturbed optimization problem we need to look at when we want to ask the question, when does ISS actually imply certain regularity notion? When does ISS become necessary? No, sufficient, sorry. So when does regularity become necessary for input to state stability properties? And now we can exactly do this. What's happening if our generalized Newton's method is ISS? We propagate this through. We add the perturbance up there, just is additive by the way we added the perturbation to our KKT conditions and to our optimization problem. And then if we have local input to state stability, we get by definition that any solution of our generalized equation satisfies some inequality here with the constant alpha being smaller than 1 by the power of the number of iterations we've taken as a function of how far away you've started. Again, everything is local. And yes, I'm aware this is an ISS notion that only uses linear gains, as opposed to classical general ISS where you could have K infinity comparison functions. The reason I restricted to linear constants is because all of these Lipschitz continuity concepts that we used before actually gives us this type of linear gains, vice versa. So we assume we have ISS. Now, if we have a fixed point to our generalized Newton's method, fixed point being we give the solution in, we get the same solution out for a given perturbation. Suppose we had such a fixed point, we add it into our inequality, we take the limit, because the fixed point isn't going to change, we take the limit, we end up with a Kalmus condition on the fixed point of our generalized Newton's method as a function of the norm of the perturbation. And this calmness condition, well, okay, no, let me add this too. Any fixed point of the generalized Newton's method, by the way we construct the generalized Newton's method, also is a solution to our KKT condition. So again, we look at the perturbed KKT conditions. Any solution to the perturbed KKT conditions, again, satisfy the same inequality. So we have calmness also in the solutions to the perturbed KKT conditions. And because we have this calmness here in the solutions, we can conclude that our set value mapping is what is called strongly subregular. Now you can imagine strong subregularity is a condition weaker than strong regularity. So strong regularity is not necessary for ISS. We could have assumed strong subregularity all along. The issue with this assumption is that strong subregularity, while it guarantees us stable convergence of our generalized Newton's method, it does not guarantee us existence to the solution. We only have a set inequality here. We assume that this inequality holds for all possible iterations generated by the generalized Newton's method, but those iterations might not exist. The reason we previously used strong regularity in our derivation was that strong regularity also guarantees us existence of solutions to the generalized Newton's method. But, and that's the nice thing, we can formulate a stronger ISS notion, which is actually necessary for strong regularity. And in fact, it's necessary and sufficient. I call this a conjecture, not because I cannot prove it, but just because I just haven't written up the proof carefully and it hasn't been submitted nor reviewed nor anything. So take it with a grain of salt, but I'm quite confident that the result is true. So we have these necessary and sufficient condition for input to states for strong regularity in the KKT conditions in the form of what is essentially an incremental ISS notion. So here now we are not looking anymore at the distance between any possible solution and the optimal solution we want to find, but actually at any two pairs of sequences generated by the generalized Newton's method. Okay, I think I'm running out of, well, I already spoke for an hour. Wow. Just some concluding remarks. Regularity is a quite rich framework that allows us to derive all kinds of sensitivity and stability results, not only in terms of systems theory, but also in terms of differentiability of optimal value functions, optimal solutions, etc. We can relate it to stability notions of stationary conditions and other second-order sufficiency conditions that have been developed for nonlinear programs. And the nice thing here is, and the reason I'm looking at it partially is, it transcends into more complicated nonlinear problems, for example, those that involve not element-wise inequalities, but actually maybe STP, semi-definite programming, sum of squares constraints, etc. It's a very rich framework that applies to very general optimization problems. Strong regularity implies incremental ISS and uniqueness, but it is a very strong notion because it implies strong incremental ISS and uniqueness. There are some alternatives, such as strong subregularity and metric regularity. Problems here, that's kind of the future work part. Strong subregularity, we've seen, implies ISS, but it does not guarantee us existence of solutions. Metric regularity does guarantee us existence, but it only guarantees us the existence of a convergent solution. There might exist other solutions generated also locally that do not converge. So strong regularity right now is pretty much this in-between notion that does both of the two. And part of the future work will be to find weaker notions that still give us sufficient stability notions on the generalized Newton's method, in particular in the presence of non-unique optimal solutions. With that, I'm at the end. Has been a long journey. A couple of people have been involved here one way or the other. They might find themselves in these pictures. Everyone else thank you very much for showing up, listening. And if there are any more questions, I'd happy to engage in a discussion. I'll also be around for a few more days next week. So if in the middle of the night next weekend you have a question, you can just email me and we can meet for a coffee and discuss all your questions. Thank you very much.
Questions?
Hi, very nice talk.
Thanks.
So I have kind of a high level intuition question. So you have a function that you're optimizing, and then you have a feasible region, which may or may not be given with functions that might be just a set. So how do these notions of stability and regularity kind of trade off the properties of the function versus the geometry of the set? Right. So like if your set is nice and plump and round, can that potentially compensate by the function being poorly behaved to some extent? And vice versa. Like if the set has sharp corners and like narrow edges or whatever that means, if the function is really well behaved and maybe is not too sensitive to perturbations, they can kind of compensate for each other's deficiencies.
Most certainly. I mean, the two come together in this generalized equation through the normal cone mapping, right? So I suppose if your normal cone mapping was somewhat well-defined, it could compensate for the cost function and vice versa. So I'm pretty sure that this is the case. Now, maybe the disadvantage of this concept here, it's fairly general. That's why we can apply it to so many problems. But it also means that if the problem is very general, we have a hard time kind of evaluating on a pen and paper basis whether strong regularity holds. If we have a nonlinear program, we can go over active constraints, and we have basically some subspaces on which some gradient must be positive. If it's a very difficult constraint set, then establishing that we have regularity in the first place is probably a difficult question in itself. So that's probably even true if you had a nice cost function and a somewhat nice constraint set, and it probably gets just worse if either of the two isn't nice anymore. But I'm pretty sure that you have some kind of compensation in there. Yeah. Yeah.
Hey, thank you for the talk.
Yeah.
I had a question about generalized Newton iterations. It seemed like that was one of the kind of foundational things of your talk. So I assume this takes regular Newton's method as a special case.
Yeah.
But I'm wondering, like, what are the other special cases of generalized Newton iterations, and like, why would you use something else besides like regular?
Yeah. Yeah. So take Newton's method. Obviously, as I've shown you, it takes also SQP, SLP, projected gradient, virtually any quasi-Newton method, so where you just approximate the Hessian. We've extended this to some fairly strange concept where you had basically a multi-step Newton's method. And you can show that the augmented Lagrangian method fits into that framework. So virtually speaking, ALM is another type of generalized Newton's method. Don't quote me here because, well, you have to do a little bit of math in between, but the same result holds. You've got Newton's method on the basis of interior point methods. I haven't worked that out, but I'm fairly sure that you can derive results from here. We've been looking at ADMM, which is a little bit on the weirdly behaving side because you add a level of inexactness in your ADMM derivation. So it's not exactly some kind of Newton method, but it looks very similar too. I'm actually running out of optimization methods here.
Would you say there are any like very popular optimization methods that don't fit into generalized Newton?
If it's gradient based, I would be very curious to see one. If it's not gradient based, then obviously, no, it's not Newton. And if it was like, I don't know, genetic algorithms. Sorry?
The new one.
Yeah. I mean, there are very strange ones, of course, or maybe you have a combinatorial problem. I'm not going to say any optimization algorithm is Newton's. But if you look at gradient-based problems for nonlinear problems, which follow in this framework, then it looks like a lot of optimization algorithms fall into this framework, and they somehow boil down to Newton, one way or the other. Yeah. Yeah.
So on that topic, would the notion of stability and regularity have different interpretations when you're trying to fit different algorithms into this framework, right? So like the classic Newton method, if you start close enough to the optimal solution, it'll just converge.
Yeah.
A gradient descent algorithm, you need to do something clever with a step size for it.
Yeah.
To converge, right? So like, can you kind of reinterpret this notion of do we not need a step size with certain properties back into this?
Yeah, indeed. So classical Newton converges if your Hessian is sufficiently well defined, typically if it's non-singular, which is exactly strong regularity for a function.
Right. But
and your step size, it's a very interesting problem. You go back to the main theorem. Your step size, that's actually interesting. There's another version how you can derive this, and you get a slightly different result. But in the way we formulated it here, strong regularity would hold for any positive step size. That's because how we introduced this H operator for projected gradient. But the step size becomes relevant when you derive this Lipschitz constant here, because this Lipschitz constant describes how well the operator H describes locally your nonlinear first order necessary conditions. And if you would develop this for the particular case, then you would basically get your normal condition on the step size selection for a projected gradient to ensure convergence.
Looks like you're over time. Thank you very much.
Yeah.
Very questions.
Yeah. Thank you.
Yeah.
Guess I'm just.
Hey.
Hey.
Very interesting topic.
Thank you. And let me just a second. Basilius, should I just stop the meeting or end the recording, or how do we do it?
AMS.
Yeah.
Okay.
Oh, interesting. What does that stand for?
Maybe we're talking about confidential research and it shouldn't be on the YouTube channel.